B basis functions by different orders. So single A product, so up to 15 functions. Then we have product of 2 A's, and that would be all possible permutations, symmetrically invariant, up to multi-index N3 and L index 3, and so on and so on. So it's just limited one, and it's give us 68 functions. Typical size for the production, 700, 1000. Right, but because we have small data sets, I don't want to have the over-determinate or under-determinate system. Otherwise, that would not work. So, yes. Exactly. So it's good that you go in front of me. I learned that you have to restart your environment. Okay, now on the same page. So you have to restart your environment while virtual machine is already set up and installed. You can just continue running from here. I don't know why. So yes, and after that it should be okay. Right. Okay, now we're good to go. So let's load this data frame. Compute volume and volume per atom, total number of structures and atoms. Do the plot. Set up the basis set, and we define the function that will compute. So for those of you who would like to later use these B descriptors, there is compute B projections function, which we export above, that actually give you the dictionary of projections for each species type. I have to say that basis functions are atom center specific. So we have subset of basis functions centered of copper, centered on aluminum. We would have aluminum data set and so data and so on. So that will be split into this dictionary. And if you want to keep track which structure is what, because you will have B projections for each atom in a structure, but it will be just one big array, an NumPy array. If you want to keep track of that, there will be also parallel mapping of structure indices. But skipping all the details, this function will give us the compute energy design matrix, which looks like that. So you can see 105 rows, each for, yeah, so I have to say that even since we compute projections for each atom later, here I group by structure index and just take an average value of the functions, like pretending that I sum up the atomic sites energy contributions to the total energy per atom of the system. I mean, it's just mathematical transformation. So that's why I end up with 105 rows, and we have 68 columns, so for each basis function. And as you can see, so for example, higher order basis functions, they close to 0. Just because this data set is not that diverse and highly symmetric. That's why these high order functions, they could be close to 0, but it's just a problem of the particular data set. So we have our design matrix X, and target property will be energy per atom. You see energy corrected. Corrected actually means that we subtract single atom energy, because that was FHIM's data, full electron code. Single atom energy is minus few 100,000 of electron volts. And so for linear and nonlinear fitting, it's better to have something in the reasonable range within plus minus 1 to 10 EV per atom around 0. That's why we just do the constant shift. It's just details. Okay, now that will be our training set. Let's generate the test one with extrapolation. For that, I will use AC. I create FCC primitive cell, one atom, and I will do the volume range from 50% to, let's say, a factor of 10 of original volume. I generate these AC atoms by just rescaling the atom cell, and I will compute the same design matrix, but for that. So now I have 250 test structures and the same 68 functions. Okay, now we'll start with the fitting of the linear model. The simplest one, we just have some helper functions that will do the fit and predict and visualize. I just don't want to repeat the code. but it's nothing spectacular here. And we start from linear regression from scikit-learn, which, as we already mentioned in the previous, before break, it's the simplest possible linear model. It has no regularization. It has closed form solution. That's actually what it's doing for finding the coefficient. So that's the closed form solution for that. Important option that I said, fit intercept false, because if I assume that my atoms do not interact at large distance, so if I have no atom, I should have zero energy of the system. If I have this free term intercept, it's called intercept in linear model, then it's breaks this. So I switch it off. And if I fit the model, you will see them. Okay, I have to import, sorry, skip one line. I fit them, or I create the model and I call fit predict. So first we will take a look on the histogram of linear regression coefficients and take a look on the scale, 1 million. So the non-regularized fit for this small data set with such amount of function is overfitted. That's why we have such a big coefficients. So actually we have quite low error, test error for energy. It's sub-milli EV, and it's predict, so the classical pair plot true DFT versus predicted ACE with linear regression is strict diagonal, nothing good. But if we now compute prediction of this model on the test set, you can see, so this is energy versus volume per atom. That's the region where we actually have training data, and that's how it behaves outside. So you ask me about how about this false minima? Here they are. If you have bad choice, non-regularized fits, and limited data set, doesn't matter which function do you use. If it's not physically inspired EIM or MIM or so, then you get garbage in, garbage out principle. So how to tackle with this? We don't speak about uncertainty indication yet. It's just simple fit. We can do regularization. Basically, it means that we have a loss function where, in addition to residuals, we have some penalty term which restrict the spread of drainable coefficient. I mean, it's classical thing, nothing new. It could be L2 norm, it could be L1 norm. For example, I use reach, which stands for L2 norm. And we can specify this alpha parameter here. So this is it. You see, if it's very small, then it's slightly regularized. If it's very large, it will be over regularized. You can play with that. That will be part of your task. So if you do this fit now, the spread of coefficients is good. It's within plus minus 1. Force RMS energy RMSC 0.5. We still see diagonal, and for this extrapolation, well, at least it's better than before, but not that good. Maybe we can, or you can, change this parameter here, try to increase it. Feel free to change this by order of magnitudes. Try 10 to minus 10 or 10 to minus 3 or just 0. You will see how it will change. In the meantime, for example, another favor is elastic net, which regularization of both norm L1 and norm L2 and the balance between. Again, I use fit intercept false. And you had just, well, something a little bit more physical, but still not that good, because now it has overshooting here. Yeah, so you can try, let's say, 5 minutes, because it's just as simple as changing numbers here and rerun this code, or changing numbers here and rerun this code. Try to maybe build more physical model, or maybe to expect more physical behavior, that it has no minimum maxima. So just take your 5-minute time and try to do it. That's actually this task. So let me also try to change something. Let's say if I go to the over regularization regime and 10 to plus 1, how it would look like. Well, it looks in principle physical, but you can see it's 31 milliV per atom and there is no diagonal correlation. So that's over regularized model and it's not flexible enough. So in a normal, the right way of doing machine learning, you have to do the train test split or even the cross validation since data set is small and then do the hyperparameter optimization and so on and so on. But that's not the topic of today's tutorial. You can just play with that particularly and feel how it's influenced. But for example, you can see when we put more and more regularizations, then it's became, well, it's changed the scale, but it's close to what we expect. Okay, and this is still a linear model with different favor of regularization. And we can move further to the model with uncertainties. And for that, there is another helper function, which will plot a little bit more fancy plots. And we will start from the simplest approach is ensembling. And in ensembling, we, instead of one model, we have multiple of them. But the data on which that was trained, that could be generated with so-called bootstrapping and aggregation, so bagging. Actually, in scikit-learn, there is built-in class called bagging regressor. Unfortunately, that doesn't provide the standard deviation of the prediction from ensemble. So we need to hack this class and extend it. That's what we do. So I just do the another subclass from the original one, and basically I copy paste the original predict function from that class, and instead of return only averaging, I also return std of that if I have this request for return std of the predict method, right? And all the bootstrapping, splitting on the data set and so on, that will be done in the original bagging regressor class. We just a little bit improve its functionality. So let's see what we get. So here I will create an ensemble of 10 rich regressors. So first I create a rich regressor, again, some my selection of alpha, fit and intercept false. But then this stuff I put inside my new class, and I say I want to have 10 estimators. I would like to have all the features always. I would like to have the bootstrapping, meaning I will internally, it will generate 10 subsamples of the same size as the original data set, and some fixed random state for reproducibility, of course. And now, if we execute this, what do we see? So first of all, the average prediction, perfect pair plot, diagonal line, less than 1 milliV error. What should we expect else? But now, if we look, it's important to understand this plot. So here we have our train data set. So it's a range of volume, and that's a prediction. But we also have plus minus sigma, and sigma in that case, in case of ensemble, is a standard deviation of ensemble predictions. And you can see, so this is like overlapping, and this is just uncertainty in the log scale. You see that in the training region here, uncertainty is small. But once we go outside, it's increased exponentially. So disagreement between different estimators of ensemble increase. And even with the linear model, you can see that it indicates some extrapolation at larger and smaller volumes. So it works basically. So yeah, you can try to switch off. Yes? Yes. So we have some cutoff, which I think 6 angstrom. And outside this cutoff, function goes to 0. It means that they doesn't matter what all B functions just go to 0, and disagreement between zeros is 0. But it has physical sense because we expect at long distance dissociation, we have just go to the 0 limit. So I would say that's a by physical construction or physically inspired construction of the framework. Yeah. So you can try to switch off the bootstrap option here. And in that case, the model, all 10 models will be trained on the original set. And as you could imagine, because that's a non-stochastic closed form solution would be always the same. If you repeat it 10 times, it still will be the same. So no any disagreement. And we expect to see no uncertainty indication at all. Again, we have perfect agreement between train and test. But if you look on the sigma, it's numerical noise, 10 to minus 15. So no disagreement because we did not randomize. We did not randomize our training data. However, let's say, just the average prediction is still similar to what we had before, but now we have no uncertainty. So that's why diversity matters. I put it back to true. You can try to also play with another regressors here. So instead of rich, you can use lasso or just linear model and so on. But in principle, that should work in the similar manner. Okay, that was ensembling. And that was like frequentist approach to sample uncertainty and coefficients and the models. But now let's move to the more exact solution in the Bayesian framework, mean Bayesian linear regression, or it's called Bayesian rich in scikit-learn. And it's easy to use, so you just call import, set it up, feed, and actually just repetition of the same mass from the slides from the previous, before the break, we covered that. So actually this is a 68 coefficients, which is computed in such a manner. So this is a design matrix, this is a target property T. This is some SN matrix, which is computed in such a way, sigma. And that's a 68 by 68 matrix by itself. Why 68? Because we have 68 basis functions. And to make the new prediction, we can, yeah, okay. These two guys here, they define the distribution. Actually, that's multivariate normal distribution over the parameters. And you can even sample from this distribution, for example, numpy random.multivariate normal. You can provide these coefficients as the mean and covariance sigma from Bayesian regression. Let's say I ask to sample 500 random version of that. So I have 500 samples for each of my trainable coefficients. And for example, let's consider function number 15. We just plot the histogram of the parameters for function number 15. What we can learn. So actually, this is because we sample from the Gaussian distribution. Yeah, it looks more or less Gaussian. It's centered not at 0, so 0 is here. Since it's centered not at 0, we can, let's say, if you know what is the p-value when you fit the linear models, then it's actually the like one side of that. So it's, let's say, small probability that it's really occasionally have non-zero value. So mostly likely this is really important function number 15 because its distribution is shifted away from 0. That's a question of interpretation. We would not go too deep to that. Contrary, for example, consider function number 67. You see it's centered around 0, so it's just probably not important function, and even if it's plus or minus, it does not correspond too much. And we can now, in principle, make a predictions. But again, to making the prediction, we had it in the slides. We should not do this 500 samples. There is closed form solution, which means just matrix multiplication to get the actual predicted value and covariance of this value. So that's why we use our helper function, which give us again the same result. So distribution of coefficients, it's in small range, very good. Pair plot almost diagonal, it's perfect. And this is our EV and just this uncertainty on this test set. And you can see that even if the scale is different, I mean, the scale that we see here and that we've seen in the ensemble learning before. Most important point that there is some threshold above what you can say, okay, if my uncertainty more than certain value, I'm extrapolating, right? So this is Bayesian linear regression. We have fixed number of basis functions, 68. Okay, let's go now to the Gaussian process, which is like, okay, it's here on time disconnected. Does it? I think I will be disconnected. Okay, I'm already disconnected. So the ROM just went off, sorry. I think I have to go to plan B. Okay. Okay, here. Go to and share my screen and we continue. Cool. Okay, sorry for that. I just switched to Wi-Fi network. Okay, I hope it's still would respond. I hope it's not killed my session. Let's see. And yep. Okay, now it's good. Okay, we now go to Gaussian process, and so the main flexibility now you have to construct the kernels. You can use the default radial basis functions, RBF kernel, or you can use whatever you want. I don't know, mattern, which is generalization of RBF. Whatever you can play with that. I just use this particular option and again do the fit predict with my helper function with the Gaussian process. Now it has some, let's say 1 milli accuracy, but it's still okay. And we have the natural uncertainty from the Gaussian process. You can see the sigma just plateauing when it's go far outside from the training set as expected. So we have yet another way of uncertainty quantification. Now we can go to the optimality criterion, and for that I first would like to drink some water, and then I will show this geometrical interpretation. Because this active set is constructed in this hyperspace of 68-dimensional basis functions. Now it's hard to draw 68 dimensions in two-dimensional screen. And for that, we will do just for only demonstration purpose, we will do the dimensionality reduction using PCA to 2 dimensions. So for that, we use, again, another scikit-learn sub-package for PCA, and I do the projection to 2 components. Explained variance ratio is almost 99%, even in the first component, which means it's most representative. But whatever we expect, it's a very small data set. It's not that varies. And we can do the visualization of that. So here we have PCA component number 1 and number 2. So the black crosses is the train configurations. You see they located around origin, 0, 0 point. And our blue points, here is our test. You see they form some one-dimensional manifold because it's just a single volume change, only degree of freedom that we change for FCC structure. And it even goes overlapping with part of the, you can get this as a FCC part of the train set. So we go through this region. Okay, color bar here is not meaningful. but that's how we can, let's say, for demonstration purpose only, project our train and test dataset on 2 components only. So now we have to do we can compute active set using Maxwell algorithm. So for that, there is a method called compute active set from PyAce package. And it should select us the 2 points out of this bunch of black crosses, which form the maximum volume parallelogram. And we can visualize it. So that's my 2 points that was selected. And I just plot, okay, with NumPy, I will do some polygon for visualization purpose. I need to invert my matrix. So I use pseudo invert because sometimes it's could be really not ill-defined, but bad conditioned matrix. So pseudo inverse, better to use for that. And in order to compute extrapolation grade for any new, let's say, test configuration, we multiply this particular set of B-basis functions by the inversion of active set. And we do that here. So this is a max of absolute value of dot product of X test PCA times inverted active set. Nothing spectacular, just implementation of the equation above. And we can split them by gamma more than 1 and less than 1 just to highlight and color code it on the next plot. Okay, here we go. It's the same set of train points, the same PCA decomposition, but now it's highlighted. So first of all, you see the active set region, and with the blue points is exactly 2 samples that enters into this region, which forms the maximum volume parallelogram. And whatever within this parallelogram has gamma less than 1. So you can see the color bar on the right, which shows the extrapolation grade gamma. And inside this shaded region, it's all below 1 by construction. So we believe that for samples from this region, we have interpolation or reliable prediction, as well as good our model. And outside, it is marked all in red. Then we go to the extrapolation regime, gamma more than 1. So prediction could be unreliable. If we now make, okay, just do the mapping. And so this is a gamma depending on the volume of the test structures. Okay, this works. You can see that this is a gamma equal 1 threshold. In this region of volumes, when we have trained data, gamma less than 1 by construction, and that's reliable prediction region. Outside of that, in the long volume distance region or short volume region, gamma increase, and we have more or less more reliable or less reliable prediction. So it works. So, but that was just exercise on 2 components of PCA, and this is not actually how it's working. So if we really want to follow the workflow of PACE potential fitting and active set calculation, we have to compute, given the training set and giving the scoper 1 potential in YAML format, we have to compute the active set. So let's run this command. This is command line interface, actually to the same Python code that we used before, but on the original big data set. What does it do? It's okay, 1 of 5 structures, our potential. Actually, it has 53 functions only, so 368 atoms in total. It's just check how much memory it would use. On this virtual machine, we have 9 GB of memory, so it will fit it, do it all in one shot. It computes the projections, computes the active set, do the inversion, and save it to this ASI file, active set inverted. So now we can use from PyAce package, we can load this YAML potential file as well as corresponding active set and do the typical classical calculations that ME6 simulation environment. So let's say we load PyAce calculator with this potential. So this potential was fitted with PaceMaker before, you just have it as this input for this tutorial. And we load the active set, and we create, for example, copper FCC structure. Again, we set the calculator, we call get potential energy. That's our potential energy. We call get forces. It's all zeros because it's symmetric FCC. What else should we expect? We call get stresses. So the first three is not that close to zero, so probably it's not really close to equilibrium, but quite close, which is good. And in addition to that, if we call corresponding calculator dot results gamma, we will get this gamma value for each atom. I mean, it's cubic FCC cell, all atoms equivalent. That's why you see all equivalent numbers. And all the less than 1 means that that was obviously part of the training set, not a big surprise. Now, let's compute the actual gamma for our original test set, which is long-range energy volume curve. I do it stupidly in the for loop, just to accumulation arrays, set the calculator. Because we use the calculator, we should do it in parallel for both energies and gamma. Algorithm is very simple. For any atom, you set the calculator, call get potential energy to compute everything, accumulate energy, get the maximum among all atoms, and also accumulate it in another list, and we can visualize it. Yes. So this is it. So actually, this is again, we have this problem with bad prediction in this region because there are no data. So now it's original real ACE potential fitted on both energies and forces using nonlinear optimization and so on and so on. But it's still the same problem because there's no data there. But extrapolation rate, sorry, it's not EV per atom, it's just unitless. It's go above threshold 1. So it's clearly show. So it shows something unreliable here, but at least it's say, yes, I am not sure, gamma is very high. Right, so that's how it's supposed to work because we had training data in this narrow volume region only. Now we can do more atomistic simulations with this extrapolation rate. So for example, we will also use this active exploration, this mapping the new environments I just imported, but first thing first, let's try to imagine a situation when we want now to improve our copper 1 potential. So we need new training samples for that. How you would generate. You can run MD dynamics with lumps and so on, or you can try to use this active exploration. So I start from generating copper FCC, set this active exploration when you have to provide the original potential and original active set, and we can call this active exploration. So here I would geometrically limit the minimum distance to 1.5 angstroms. I would say that on each iteration you have to go up to gamma 100. So it's every time it will be new structures that is, let's say, have this extrapolation rate around 100. There is no limit for gamma low, and it will do it 4 times. So what does it actually do? We can read it from the logs. It's randomly choose. So in this FCC structure, we have 4 atoms. It's randomly choose atom number 2, and then it's try to move it outside of its original position. So start from 0, 0, 0, and maximum extrapolation rate within the whole structure was 0.4. We've seen that before. So it's actually the Nelder-Mead optimization. You see it's just start to accelerate, and then max gamma, even if we have quite small displacement, max gamma just explodes. So it even goes out more than 100, then it goes back to 100 because we want to do it in like regular extension, sorry. So it found that if we displace copper atom number 2 by this vector, so that's our new environment. So we recompute and construct or update active set with this new environment. So write and separate and the intermediate files, and then we can again randomly choose from another available for atoms. Actually, it should be 3, and then it's repeat, but now it's done already with respect to new updated active set. It's like within this new configuration, what else we can discover, right? It's like a long-term memory. And this procedure repeat, we say it's 4 times. So actually, we can try to visualize it with NGL view. I hope that would work, but slow, that should work. Yes. So you can see the slider here. This is our steps of active exploration. The first is one is the original FCC structure. It's all, let me try to put it full screen. Yep, and make it larger. So, but actually for this copper one, because it's so limited training set, so even the smallest displacement that was just fraction of angstrom already brings it to new environment. I mean, it's like a newborn baby know nothing about world, and it's just a surprise for everything. So that's why if you move to the last iteration, you probably have seen it's shifted by very tiny amount of very tiny displacement. So it still looks like FCC, but actually if you play back and forth with the slider, so this is new structure for this newborn potential. Right, so in an ideal case, you have to generate several samples like that to expand, but practically because, so what is gamma? Gamma is the relative change of the volume. And if we start from the small original active set and we change it by factor of, which is gamma high 100 by factor of 100, it's still not that big. If we'll repeat this procedure, then it will be exponentially increase, and you will discover more and more configurations. So at the beginning, at the early stage, that would be as efficient as that, just to do some random displacement of the atoms, which will give you in principle the same amount of information. So it's not that spectacular. But what if we try to do it? Yeah, it's written here, no large displacements are observed because copper one were trained on ideal structures, and any out of equilibrium is already a surprise for that. Let's try more advanced version of potential on the copper 2 dataset. And we just, again, you have loaded before copper 2 B basis potential and a corresponding active set. So we will do the same setup and we do visualization. Okay, so the snippet could be closed. First, in this logs, you can see that sometimes there is too small distance, because I put 1.5 angstrom as a minimum distance to geometrically constrain that. Because large displacements was already covered in this data set, and problems can start in this low distance region when usually atoms should repel, but if there is no data, it can be just energy can goes down and it just collides. So let's start to discover this region of atomic environments. But since we limit, it could not go closer than 1.5 angstrom, but this is physically inspired, so just material dependent. Sometimes it's need to restart or shake the positions just to maybe get the Snell-Dermit out of the local minima, and finally it's find some configuration. And what is interesting now, if I again go to the full screen and just displace it up to the last, you see how large was displacement from the original ideal FCC. Because that potential has some experience with different atomic environments, so we require much more displacement of atoms to surprise us that it will find the new configurations. And again, since we can repeat it several times, we can generate samples, go to do DFT, get reference energy forces for that, and then upfit existing potential and then repeat it. And this is your active learning scheme, classical one. Okay. So let's go a little bit more atomistic advance and consider the point defects, vacancy and vacancy migration. So I would say that, for example, single point vacancy, I think that was part of the training set, but we didn't add, I just remember how we created this training set for copper to potential. We had no vacancy migration transition state. Yeah, so let's see if this active set will be able to recover this. Yeah, so what we do, so here I would use this NAB, neutral elastic band method, which implemented also on AEC in order to compute the vacancy migration. Again, instantiate calculator, set active set, but you can use this calculator even without active set. That will be just energy forces stresses for in your simulation. It's optional. So we create a supercell 2 by 2 by 2. According to this neutral elastic band tutorial from AC, you can find it here. We need to create initial and final. So in initial configuration, I delete atom number 0 and the final atom number 1, just to have two adjacent vacancies, and then interpolate between them. I mean, it will be done by NAB. And I have to set up the separate copy of calculator for each of image. That's how it works. So you see here, we do not set up any active set, we just compute energies and forces. And run this NAB minimization. Okay, it's done. And now what I will gonna do, I go over all my NAB images and I will collect energy and this max gamma as well. Put it in NumPy array and do some plotting. And here we go. So that's our profile of NAB. So I have to say we didn't do relaxation of original vacancy here, so probably it have to be shifted a little bit below, but it's just technical details. And for these endpoints, when we have perfect vacancy in position of atom number 0, atom number 1, extrapolation rate is close to 1, even below, because that was in the training set. We put it explicitly. But the extrapolation happens in between. When we go to the transition point, you see gamma increase up to 6. Actually, if you Google for vacancy migration of copper FCC, that would be more or less realistic value, I would say. Maybe it's 0.8 or 0.9. Don't remember, to be honest. But it's not that bad. But still, potential in this active set signalize that it's not sure about this prediction. So in the ideal case, you have to take the structure and go to the DFT and like update your training set. Okay, I think I ran through all the notebook, and now just a few tasks that for the rest of the time, I don't know how much do we have. How much time do we have still? Yeah, then it's perfectly fine. Then you're free to try and discover what else was in our training set for this copper to potential. So for example, some ideas to try. You can create surfaces with AC. So just check this link. There is a build sub package. You can create FCC, just put copper here, set calculator, and compute potential energy, and then check this gamma and see if it's more or less than 1. So, or you can try to, what else? Create a D vacancy, so just remove 2 adjacent atoms simultaneously and check if it's more or less than 1. Or for example, you can put interstitials. So for example, if you create 2 by 2 by 2 supercell and add 1 atom at position 1, scale position 1/4, you can do it by this code snippet. So just driven by human intuition, try to find the structures that were or were not part of the training set, and if potential predicted reliable or not. I think I can start to do the first FCC surface just to show what should we expect. So for example, from ASE, that was build, import, let me check, surfaces. Okay, just copy this. But instead of aluminum, I will take copper. And I think I will put also periodic equal to true. Yes. So we can even view this slab using viewer NGL. So that's our surface. I mean, it's not that big, so you, for example, can add more layers here and make it like that. Yeah, so now it's 4 layers of atoms. And then it should be as simple as, so let's say my slab dot set calculator. I think that was the calc name for that. And that is already with attached active set. So I can say slab get potential energy. It will give me some potential energy. I can check the forces and so on. But what I'm interested now, so in the calculator that I just set, it has actually the results dictionary, which contains everything: energies, forces, stresses, and we're interested in this gamma. So let me just select this. So for each atom now we have this gamma, and as you can see, well, I can take a maximum of that. This is close to 1, which means actually, yes, we have the surface in the training set, and that enters into the, or close to the border of active set because gamma close to 1. So that's, let's say, reliable prediction for this structure. And the rest you can try in the remaining 10 or 15 minutes. And just to bring the reference, so the papers about this ACE, fitting of ACE and also active learning, you can find the reference here. So the last one is under revision currently, but you can find it on archive. And I would refer you to the pacemaker documentation. Again, pacemaker is the docs.io. There is even a specific section for extrapolation rate and active learning, so describing the tools and setups, as well as in the LAMPS official documentation. We have a section for extrapolation rate and all the snippets for input LAMPS scripts to make it run with LAMPS. So I think, yes, in the remaining 10 minutes, just feel free to ask your questions or play with the structure. So yeah, do whatever you want. Okay, I think we are now running out of time. So if there is no any further questions in the chat or in the audience, I think I can stop the sharing, and I'd like to thank you for your attention and efforts if you do any following the tutorial. But even if not, thank you for staying here. And yeah, so thank you very much.
All right, thank you, Yury. So I have 5 announcements, so let's see if I can I can remember all of them. So or do you want to? All right, good. So yes, so this is now the end of our tutorial part, and then next in the afternoon we are going to start with the talks. And yeah, all the tutorials, all the notebooks are now online on our website, and they will stay online for about 1 year. So was it 1 year? Yeah, so they will be there. And yeah, we have recorded all the talks or tutorials, and we will upload them or links to those to the website at some point next week. And yeah, regarding the evening, so we have an in-person poster session in the evening for those who are attending in person, and the poster boards are already in the coffee area, so please feel free to set up your posters whenever you are ready. And yeah, I hope that yes, final thing. So next it's a lunch break. We will gather here again. Was it 1:40? Yes. And so it's in 1 hour and 20 minutes. And yeah, the nearest cafeteria is second floor, this building. So you need to go down to the lobby and then take the stairs up. And those who want to have lunch, so we have a cabinet booked for us. So unfortunately, you have to pay for the lunch by yourself, but you can go to the cabinet and we can sit together. And then we have to return the dishes to the dish collection point afterwards. Did I forget anything? Probably not. Yes. Okay. Thank you very much.
Yeah, let me just add since you're already registered, you don't have to be here quite as, at 22. I think we start maybe at 10:02 with the opening remarks, which to a large degree you've already heard. And I just passed the Swedish Student Union building, which is on the other side of this building. And I realized it's Wednesday and they have legendary all-you-can-eat spaghetti. So that's also an option. So basically you take the back door and then you go straight over to the left is the building. So that's another option for you if you wanted spaghetti. Otherwise, this building is very easy. You don't have to leave. Okay, see you again at just before 2.